Hey guys, I hope you're having a good evening. It's nice to see you. I am live in my office, same time, same place as usual, so I guess it's not surprising. I'm going to go ahead and there you are. Recopy the Pear Deck code and we'll talk a little bit about today. First, I'm just going to talk a little bit more about some stuff we did last time on Tuesday, and then I have a couple new problems to introduce, and we're done. Like, this is a pretty straightforward module. Next week, we have a holiday on Monday, so there's no class. On Thursday, I'm going to post a video recording in the module for that week of Thursday's topic, and I will just be available for extended office hours on Thursday, basically from 4:30 to 7, so that if you look, and I'll make sure, try to post the video in the morning so you can kind of, actually, maybe I'll even try to post it before Thursday, all right? So that if you have time to take a look at it and you have questions, you can get back with me. It's on absolute value equations and inequalities, which is something that you probably have studied before, but sometimes can be a little confusing. So I will post a video lesson, basically me going through a lecture, but it'll be the whole thing. I'll also put it in the notes, but I just want to make sure you have that opportunity to get the instruction, and I will be here for questions. And if you just want to even work on the homework during class time, like if you are not taking a final exam that day, you're more than welcome to just pop on and reach out to me if you have questions on homework, and I'll help you kind of just like an office hours one-on-one sort of situation, but it might be 1-on-7 because I don't know how many people will show up. Anyway, I hope you guys are doing okay today. I hope that some of the tension and anxiety from the beginning of this week have faded away. I have 3 or 4 more people that have taken the test, and nobody's contacted me to say that they're having issues with HonorLock. So I'm like, I think we got the settings right, and I just believe we're going to get there, guys. I believe it. So anyway, without further ado, here, wait, actually, oh, I did have further ado. There we are. I further did post the Pear Deck code again. I am going to jump into today's lesson. So today, we are going to do one more example from kind of the end of what we did on Tuesday. We're going to identify some characteristics of a function that's given as an equation. And unless you have like a linear equation, there's really, which doesn't have a minimum or maximum, it's just a line that goes infinitely in both directions. So unless you have a linear equation, there's not really a way that we've talked about in class to be able to answer questions like this one without graphing. So if I am asked to find increasing, decreasing, minimum, and maximum, the first thing you should do is graph this function, all right? So that's the sort of example we have here. It says estimate the local extrema. That means minimum and maximums. I do not like that color. There we go. So this is our minimums and maximums of the function g of x equals -2 times x cubed plus 6x squared plus 210x minus 10, and the intervals on which that function g is increasing and decreasing. So what we're going to do, is graph this function. I'm going to open up Desmos. I'll open it up here on the left so that we can still see that function. And I'm just going to type in what I have. I've got y equals -2x cubed plus 6x squared. Oh, I put y minus. Plus 210x minus 10. And it looks like it's just a vertical line. It's not. That's a lie. What we're going to do is I'm just going to adjust my y to be like something like 1,000 on top. Let's see if that makes it big enough to be able to see. Nope, I'm going to make it, actually, let me zoom out of it. I can start to see the shape. Oh, there we go. There we go. Oh no, come back. There we are. So it's kind of important that you get to see a good image of the points. I'm going to drag my cursor over here to see if there's any places where I have peaks or valleys. Okay, so I'm going to take a picture of this graph and I will click on this little button here. Look, if you get really close, you can see the 0, -10 is on here. Sorry, when I take a picture, if I zoom out, it's not going to let me like. It's not going to let me keep that point on there, so it's important that I sort of have it. And this is 0.0476. So what I wanted to show a little bit about this is we want to make sure that we, like the y-intercept is automatically going to be grayed out, but so is this x-intercept here. And so we just want to make sure that we get the correct inflection point, like the point where we change from increasing to decreasing. I want to make sure that we can see that really clearly. So for just a second, I'm just kind of going through this real fast. .0476, okay. So now when I zoom back out, yeah, I'm going to zoom back out. I want to make sure that I can see where that point is changing concavity. Okay. And either way, it looks like it's when x is about 0. Oh my word. Okay. So I'm going to get a picture of this so I can write it. Like, I don't know why this graph gave me so much grief because I am like very sad about it.
Really quick, Miss Paula, I just got in here. What exactly are we doing? Miss Paula?
You know, sometimes tech just works for you and other times it makes you look like a bumbling oaf. I know. All right.
Hello?
All right. So here,
Jordan, we're basically going over
what
what we went over yesterday, Jordan.
Is you want to graph them and then kind of zoom in and
today?
out until you can get a good picture of the graph so we know what's going on. For the purpose of this problem, I'm going to assume that the place that this makes a change in concavity is right here at -10, when y is -10. So when I'm answering this, there is no local max or min. Y'all, I can't believe I did this with you guys watching. Look at the difference. -2x cubed. Look how everything changed. Shocks. Shocking. Shocking. I'm so sorry. Okay, there we are. You still want to do all those things that I said, but now we actually have something interesting to look at. I was so concerned with why this problem taken straight from homework was going to be so bland. And so I appreciate your patience on this. But now we have something legit. Alrighty. That's right here. I'm just going to put it right on top for now. All right. So when I am talking about local max and min, that was a lot, right? So when we're talking about local maximum, that's this point right here, where I go from increasing to decreasing and I have a peak at the top of the hill. The maximum is 1068. And that happens when x is equal to 7. The minimum is -660. And that happens when x is -5. So the reason I wanted to show this is that when you see a graph like this, you're not expected to know the minimum and maximum. Okay, so All right, I see I've gotten a couple of questions in the chat. Jordan, yes, we're going to over just the very end of Tuesday's work. It just took me a second to get started, to get things going smoothly. Understand if you lose power, I totally get it. And how I got the numbers, I'm looking here. This is X comma Y. My maximum is going to be a Y value. Where my maximum happens is at an X value. X tells us where to look on the graph to find a particular output. And in this case, I want to know my maximum output that is just where I go from increasing to decreasing. So when I look at my max, I'm looking for the top of a hill where I'm increasing on one side and decreasing on the other. Then I know that I've maxed out my Y somewhere. It's not maybe the largest Y overall, and you'll see this has no global maximum or minimum, but it is the largest at this little peak. So then, so my 7 comes from the X coordinate. My 1068 came from that Y coordinate at the max. On the other hand, the minimum, we're looking here at this point, my minimum value, my Y value being negative 660, and my X value being the X where it's located. All right. So G is increasing. If I were to drop a marble along this path, right, it's increasing anywhere that it's going uphill. So in terms of increasing, it's increasing only right here between this X equals -5, which I got from the point where it was like at the minimum, all the way up to where X equals 7. And so when we answer these, we're looking for an interval. That means I'm going to be using interval notation. I'm starting at -5 and I'm going up to +7 on X. I always use parentheses because I can't be increasing or decreasing at a beginning or an end point, only like throughout the interval, implying some sort of movement. I would like you guys to write the 2 different intervals where this function is decreasing now, and you can go on Pear Deck and do that. And I'm watching people get started over here. I'll start looking and seeing what we got going on. Abigail, that's right. I'm sorry you're sad face today, Abigail. And I see you're still working on it, Sebastian. And Ruben, I see you're still working on that part D. Spencer, your intervals are you need to start with the small number on the left. So your first interval should be swapped in order. And in your second interval, it's positive infinity. But you're doing fine. Rohan, 7 to infinity is correct. And I don't know if you're still working. Oh, here, I'll drop it. Carlos to go. And oh, oops, I just sent that to one student instead of to everyone. There we are. Yeah, this is a day where I'm really glad that you guys have an online class, because I don't want you driving to get here, and I'm really glad you don't have to. All right, so G of X is decreasing as we move in from negative infinity up all the way until we get to -5. But then it's decreasing again on the right side here. starting at x equals 7 and going all the way on to infinity. Right, so that's what we're looking at right there. Noise. Nice row, huh? We're good, we're good. Okay. Just taking a look, see if anybody else added anything or something we can look at. Right. So the main takeaway from this, and there's 3 main takeaways. The one is if you see a complicated graph and you're asked about minimums and maximums, oh my gosh, graph it, graph it, graph it. You're not expected to do that by hand. Second of all, like you need calculus to do that. It's not something you can do until like late in Calc 1. The next thing is that maximum and minimum values are always y values. You can say where those happen are the x values, but the actual maximum value is y, the actual minimum value is y. And finally, when we're talking about intervals of increasing or decreasing, we're talking about intervals of x with all parentheses. So those are the 3 things I hope you gained from Tuesday's lesson and just were able to just briefly touch back in with today. There's 2 ideas that are new for the day though, and those are what we're going to talk about now. The first is optimization, and we did one of these on Tuesday, but I'm going to go over kind of a complex example that gives some people grief. So I think by going over it, it'll help you a lot when you're doing your homework. So when you're given a word problem and you are asked to actually write an equation to represent the situation, we kind of go through this modeling process. We start by making a diagram. If you are asked to find some physical property like perimeter, area, volume, circumference, something like that, start with a picture. Then you're going to read through every single thing that you have in that problem that you're given, and you're going to add whatever you can to the diagram and whatever you can figure out so that you get as many pieces of that diagram labeled as possible from the information you're given. Then you're going to write down any formulas you need. Like I said, perimeter, area, volume, these are the sort of things that we need to, like that we need a diagram for. Those are also the things where you want to write down the formula for that shape or that diagram for area, volume, whatever's relevant to the problem. Then once you get an equation based on your diagram using a formula, you'll graph it and you'll solve just like we just did in this last problem, except that instead of being given an equation, you're going to write an equation. So that's what we're going to do. And this is the example we went over before. You were given an equation. This is the example we're going to talk about today. It actually looks like this, but we're going to start with like a concept building example. So I brought some props. Let me get ready here. Just take a second. Oh no. Back up. And instead of screen sharing, I'm going to turn on my camera. And I want you, I'm going to put on a spotlight of this camera. Let me turn my little camera around. All right. So this is a 9 by 15 centimeter. This is a 9 by 15 centimeter grid. Sorry, that Post-it was there just so I know exactly where to hold my hands while I'm doing this. So this is 9 centimeters by 15 centimeters. And the problem we're being asked about wants us to cut 2 centimeter squares out of each corner. So I'm going to come on here and I am going to cut 2 centimeter squares from each corner. This one's, it's a little funky because my grid's not perfectly centered. But I think it'll be all right. There we are. And the question is, if I were to turn this piece of paper into a box. I want to find the volume of the box. All right. Now, I don't know if you've ever done something like this. If you like to bake, right, you may try lining like a brownie pan or some sort of baking dish with parchment paper. This is like a classic way to make a box. So what we do is we fold on each of these lines so that I'm left with 4 little tabs that pop up. So it looks like this. So what I create is a box. How deep is that box? How many centimeters deep? Each of these boxes is 1 centimeter. You can type into the chat, or you can unmute and say something out loud.
It's
2?
2 centimeters deep.
So how deep is this box?
2 centimeters. Wouldn't it?
Yep, 2 centimeters deep. How wide from like here to here? How wide is this box?
15 centimeters?
Wait, no, you took off 2 centimeters off of each edge, so it would be like 13 centimeters?
When it started, it was 15 centimeters wide.
Wait, you took
And
it
I
off
cut
both sides,
2 centimeters
so,
from the left and 2 centimeters
Yeah, so
from the
it's-
right.
yeah.
That's right. It comes out to 11. How tall is it?
5? Yeah. Because you took out 4 centimeters in total, so it would be 5 in height, so to speak.
It started off as 9,
You took away 4 in total.
but then I cut 2 centimeters from the top and 2 centimeters from the bottom. So what is this height right here? I'm not going to just do it. I'm waiting for somebody to say it.
It's 5. Teacher, it's 5.
Oh, I definitely can't hear you. Isn't that weird? I was like, why is everybody so quiet today? Here, let me check my settings. You guys are like shouting. Wait, hold on, let me see here. Huh. All right. No wonder. It makes me feel a little better that that's why it's so quiet. I still can't hear you guys, but I'm getting closer to being able to hear you. So weird because I can tell that my mic is working. And you may just have to do chat, but I'm just going to give it a little. All right. Let's see if that helped. All right, so it didn't help. So I am not able to hear you. The original height was 9 centimeters. So we're just going to have to communicate through chat. And I won't ask you to do too much where you have to like talk to me, but now it's 5. Guys, thank you for your patience. I didn't realize that I couldn't hear you. This is 5 centimeters. And my 5 centimeters was my 9 that started minus these 2 and minus these 2. All right. So all of this is to say the following. I'm going to take a picture. Actually, I don't even need to. I'm just going to share my screen. 1 second. All right. stop my video. So when I come back over here to the notes, this, oh, I almost wrote with a marker on my iPad. This 9 by 15 centimeter, when I cut out my corners, resulted in a box that was 9 minus 2 equals 5 centimeters by 11, which was 15 minus 2 centimeters. Right, and it turns in to this box that looks something like this, where my height was 2, my width was 5, and my length was 11. All of these in centimeters. So the volume of the box is given by volume equals length times width times height. This is where I talk about writing a formula. Oh, I want to unspotlight. All right, so that was my length times width times height, which in this case was 11 times 5 times 2. 11 times 5 is 55, times 2 is 110. Centimeters cubed, because this was centimeters times centimeters times centimeters equals centimeters cubed. So the reason I'm doing that is that the sort of problem that you're going to see in homework is like this, but instead of giving you the heights, like it'll give you the original dimensions, but it's not going to tell you to cut sides of length 2. It's going to tell you to cut sides of length x. So coming down here, this is an example very similar to a homework problem. It's slightly different. This is a rectangle. In homework, it's a square, so both sides are the same. But here we have a 5 by 7 inch piece of paper, which means that the short side is 5 inches, and the height here is 7 inches. And it says that we're going to have squares of side length x cut from each of its corners. So just like I cut out squares, oh, I don't use x here because just as I cut out my corners before, instead of cutting out a 2 by 2, I'm cutting out an x by x box from each side. And then I'm using that to fold up into this box. And we're going to be using the formula volume equals length times height times width, length times width times height, sorry. But we need to find those length, width, and height. So this part of the box here corresponds to this length right here. So if the entire height was originally 7, and I cut off x and x, what is my new shorter height? And you can write on Pear Deck. This is slide 5 on Pear Deck. That's not slide 5, it is slide 6. Nice. Yes, that's right, Spencer. Good. That's right. So that height here, I see Rohan got it too. This is 7 minus x minus x. 7 minus 2 x's. Does that make sense? Because it was 7, and then I took off x and I took off x. So 7 subtract 2 x's. And we just leave it as an expression. What's the short width then? And you can write that on there. Nice Ruben, nice Destiny. It's appropriate, both Rohan and Ruben, you both put that you have your emotion for today was just blank face, but it has no mouth on that image, right? It's like a smiley face with just 2 dots for eyes and nothing. And because I can't hear you guys, it must be a little like being robbed of voice. Yeah, I see. That's right, Rohan, 5 minus 2x. Yep. This is 5 minus 2x's. And what is the height of the box here? Remember, I'm folding along these lines. So basically, I want to know this length right here, because that's going to fold up to be the height. That's right, Spencer, it's x. So now I can go over to my volume equation, and my length times my width times my height is 5 minus 2x times 7 minus 2x times x. Now I can multiply that all out, but we don't need to because I can graph it exactly like this. So what we've done is we've gotten an equation for the volume. And we're going to look for the maximum y value, the maximum volume. I'm going to start up Desmos. Our graph is actually going to look a lot like that. This is a cubic graph, and that was also a cubic graph, the last one. I know because if I multiplied it all out, I have an x and an x and an x and 3 x's total. My highest exponent is 3. So it's going to look all wibbly wobbly. I'm just going to type in here my volume, v of x is equal to 5 minus 2x. And I could totally have done this in whatever order I wanted because it's all multiplication. So I could have put my 7 minus 2x first. It's fine. Like this. And I get this graph right here. Now, this graph has no global max, but it does have like a little, like, this is kind of a complicated graph, but only part of this makes sense. Like, we don't actually need all of the parts of this graph. I'm going to add in a domain here. First of all, I only want volumes greater than 0. I only want my side lengths need to be greater than 0. So x has to be greater than 0. And if I take my little boxes that I'm cutting out and I make them as long as possible, the longest it could possibly be is 5, because if x was more than 5, then I wouldn't even have a top side. Like I wouldn't even have a width. The width of my paper is only 5. So I can't take boxes of 5. I can't even really take more than 2.5, right? Because if I cut 2.5 inches out of both sides, I would be at 0 along the top. So I'm going to let my x be less than or equal to 2.5. So this is really the only part of the graph I need to look at. You don't have to restrict the domain like this when you do it. I just want to show you this is the only part of the graph that we care about. And here, the maximum volume is 15.021. Actually feel like to paste this. I'm just going to back this up and leave it without the domain restriction. I'm going to take a little picture. And once you graph it, all you need to do is just identify that maximum value. And sometimes it'll ask what the side lengths are that would make that volume, like the lengths of x that you'd need. And that's fine, but this problem doesn't. I think the one in the homework does. So all I do is I look at that graph and I identify my maximum value. So we come over here and we can answer our maximum volume is 15.021 centimeters cubed. And that's when X is 0.959. Again, it didn't say, oh, not centimeters, inches. It didn't say to find the number of inches. But you do need to know that X is in inches and the volume is in inches cubed. So that's just one of the word problems that's kind of funky, but you don't actually have to do much solving. You just have to figure out those dimensions using a little bit of like creative logic. All right. You can easily just pull up these notes and look at them when you're trying to do a problem like this on homework, and maybe even try it first. So it's just like knock it out of the way. The only other idea for today isn't even a new idea. It's slope, but it's slope in a different way than we've seen it before. So in the past, we talked about slope as being like the tilt of a line, the change in y over the change in x. But if you don't have, this is for a line. But if you don't have a graph that's just a line, what you have is maybe a graph that looks curvy or jig-jaggy, like this. If I wanted to find the slope between any two random points on this line, that slope is called the average rate of change. So it's just the average rate of change right here. And I'm going to talk about how we get it. It's just change in output over change in input, just like slope. But because it's a slightly different looking formula, I'm going to show how we derive it. So if I have a graph that looks like this, and I want to find the slope of 2 points on that line, what I'm going to do is do my change in y and my change in x. But my change in y is my f of b minus f of a. So my y2 minus y1 is this. F of b minus f of a, like y2 minus y1, over x2 minus x1, b minus a. That. So it is, you don't have to memorize this. It's slope. It's just that it's a slope on, like on a line. A line is defined to be a graph that has a constant rate of change, meaning that the slope is the same between any 2 points. That's not the case if I picked two different points. Like if I picked, instead of the points that were on here, if I picked this point and this point, I would have a much steeper slope. And if I picked this point and this point, I would actually have a negative slope. So depending on the points that you choose, if the graph is not aligned, you have a lot of different options for what the slope could be. So you have to specify an interval for x. That's your a and b. You have to say, oh, between these 2 points or in this region, what's the average rate of change between these endpoints from a to b? So here's how it looks. We're going to use this graph of f of x to evaluate the average rate of change of f as x goes from 0 to 3. So I'm going to mark on this graph my 2 points. When x is 0, here's my point, I get 0,1. When x is 3, here's my point, I get 3,2. So to answer this question, all I need to do is find the slope between those 2 points. So go ahead and calculate that now on this slide. You can type your workout or you can write your workout, but really I just need to know the slope between those 2 points. You don't have to like write down everything there. So on average, as x increases by 1, y increases by 0.3 over that interval. You can get that as a fraction 1/3 or as a decimal. Isn't that refreshingly simple? And compared to everything else we've done, this is probably the best. Nice. Sorry, I'm just watching different people like write different stuff. Nice, 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 nice. That's right. Yeah, I saw it. All right. Sometimes you will be given an equation or a table and asked to find the average rate of change. So we will go through and look at a couple examples like that. I'm going to skip this one. That was one that I added in that wasn't like a super important one. All right. Given the tables for f and g of x and the average rate of change of f from x equals 3 to x equals 7. And then we'll find the average rate of change of g. So x equals 3 is here and x equals 7 is here. For f graph, we have this. My 2 points are 3,7 and 7,8. Right? So if I find my change in f over my change in x, then what I'm doing is I'm looking at the difference of my outputs, 8 minus 7, over the difference of my inputs, 7 minus 3. And that gives us 1/4 or 0.25. I want you guys on Pear Deck to find the average rate of change of g over that same interval. And so that's what I'd like you guys to put on yours. Instead of looking at the F column, you look at the G column. Exactly. Yes, that's right, Spencer. In this case, our average rate of change is 5/4 or 1.25. And that's very close to what that's everybody seems like for the most part, most people got it. If they didn't get it, I'm pretty sure that looking at this, like, let me know if you got a different answer. Let me know if you know what you did. Right. The I will, actually we'll do this one that I said I wasn't gonna do. But I want you guys to actually take a few minutes to do it. I didn't want to do it out, but I want you to do it. So these graphs show the populations of California and Texas over time. And you're going to find the average rate of change in the population in each state between 1970 and 2010. And then interpret the average rate of change. And this should be parts A, B, and C. It's labeled a little weird. Start here. So go ahead and go to slide 10 on Pear Deck and take a few minutes. You can work on your own piece of paper and just write in a little bit. I want you to try these. I'm hoping, let me make sure you can actually see this graph. You'll be estimating the points from the graph. You're probably not going to get a lot of whole number points. Some of them maybe, but not all of them. It's looking good, Rohan. But we'll want to go from 1970 to 2010 on both graphs. So sad to not be able to hear you guys. I can restart my computer and it'll probably be fixed, but then like, we'll restart my computer. And we'll see. I think I probably have you guys, you're just working on paper, and so I know I only have 4 people who have responded yet. And I'm pretty sure the rest of you guys are just working it out on paper and you'll add it to Pear Deck after you have a minute. I get that. Wrote down some values of points that I'm going to use. If you estimated close to that, but not exactly, that's fine. This is an estimation. As long as your estimate is pretty close to that, like probably plus or minus 1, you're fine. Like you got this. So the average rate of change in California. Right. So the 2 values that I got for the average rate of change in California was 0.45 and in Texas was 0.35. But what does that mean? Remember that when we're dealing with average rate of change, or we're dealing with slope in the context of a problem, what we need to do is interpret that slope using the units. So this means that my change in population, my units was millions of people, and my T was years. So in California, I increased by 450,000 people per year. 0.45 million is 450,000. So in California, the population increased by 0.45 million people per year. That's 450,000. All right. And in Texas, it increased by 45 or 35 million, or 0.35 million people per year. Uh, 0.35 times a million is 350,000. All right. And I don't, in part B, which is really part C, I don't have to give an exact answer here. It says which one grew more quickly between 1900 and 2000. So I'm just going to look, and I'm going to say, hey, here's 1900. And here's Texas from 1900 to 2000. Here's, whoops, I'm going to draw a line that connects, whoopsie. I'm going to draw a line that connects those 2 points. Then I'm going to do the same thing for California. And what I want to see is which line is steeper. The steeper line has the larger slope, or the larger rate of change. So California grew more quickly. Like that. All right. So it really is an exercise in calculating slope, writing it as a decimal, and then interpreting it using the units. Okay. So it is millions, my change in Y units, my change in my Y was millions of people. So my units for X, my change in X or change in T was years. I want to write it as a unit rate. That's millions of people per year, per 1 year. All right. So we're looking for the decimal or whole number version that answers this rather than the fraction when we do average rate of change. We want like a unit rate. The only other type of problem that you're going to have to do in this week's homework is problems involving the difference quotient. The difference quotient looks like this, and can you give me a thumbs up if this looks like a familiar equation at this point, if you've seen it in this class before? Yeah, like whether or not you understand it, have you been asked to calculate this before? Right, so what this is slope. But it's slope like we would do in calculus. So you've probably heard the word calculus, and many people have no idea what it is, like what type of math you'll be doing in this course called calculus that seems to be so important. Well, calculus is an analysis of functions. So it's looking at tables, graphs, and equations, really graphs and equations, and going deeper, doing a few more operations than you've already learned. Like this year, we talked about composition of functions. That was a new operation. You will do composition of functions, but you'll also do something called the derivative. And the derivative allows you to find the instantaneous rate of change rather than the average rate of change. So if I say that I am swinging a pendulum, right? And as my pendulum swings back and forth, I have it like that pendulum is moving at a different speed. Well, notice that my height over time, I'm getting high, then low, then high, then low. My height over time looks something like this. And if I want to mask the speed of or let's see, this is the height. Over time. And I want to know the speed, like the meters per second or inches per second, whatever, that this object is moving at any specific instant, say right here. What we do in calculus is we say, let this be x. And instead of defining two separate points to do average rate of change, I'm going to find some other point that's called x plus h. So that I'm adding some number h to x. And then what I'm going to do is I'm going to let x get smaller and smaller and smaller until it shrinks to 0. That's going to allow me to calculate the speed of that pendulum at every instant, not just on average between some starting and ending point. So when I calculate this slope, my y value at x is f of x, or h of x really, but we're going to keep it f for now. Whereas my y value at this red point is x plus h comma f of x plus h. And if I want to find the slope between them, then I get, this is my y2 minus y1. Here's my y2 minus y1. And then x2 minus x1 is x plus h minus x. But x minus x is just h, and that's why the denominator here is just h. So the difference quotient gives us an average rate of change, or a slope between 2 points. When you get to calculus, you'll learn how to find a limit, which will let you shrink that size of x down to, or that size of h down to 0. But you don't need to know how to do that now. That's the derivative. You'll learn that in calculus. But figuring out the algebra behind this definition of a derivative is something that really trips people up in calculus, but it's a college algebra level skill. So they try to introduce it now to get you used to looking at this ratio, so that the more you're used to calculating it, the easier that part is when you get to calculus, right? So that's why we do this. And it was a lot of effort just to explain this, but I want to let you know why this quotient comes up all the time and how you'll be expected to use it. So this slide just basically explains what I just said out loud. I'm going to show you an example. So given this function, calculate the difference quotient for this function. What we're going to do is calculate f of x plus h, and then we'll form this quotient just like we did in module 3 and in module 4. F of x plus h means that instead of x in my original function, I'm going to write x plus h in parentheses. We're almost done, guys. Don't worry. I see it. I see it. I see you. This is it. It's just slow. We got this. F of x plus h is 2 times x plus h squared plus x plus h minus 1. I'm going to square out my x plus h. It's not x squared plus h squared. I have to actually FOIL it. Like this. X times x is x squared, x times h is xh, h times x is xh, h times h is h squared. I distribute my 2. Also, I'm going to combine these two. I'm going to add them together to get 2xh. So when I distribute my 2, that's what I'm going to multiply it by. And then I'm going to multiply it by h squared. So and this is my f of x plus h. Finally, to form the difference quotient, I'm going to do f of x plus h minus f of x, this original one. So I'll subtract these 2 in the numerator and put h in the denominator. No, you stay where I put you. So there's my f of x plus h. Minus f of x means subtract everything that's in f of x. Minus 2x squared, minus x, and minus -1, all over h. I'm going to simplify this. I'm going to change each of these to be subtraction. Well, to the opposite sign. So this is the same as 2x squared plus 4xh plus 2h squared plus x plus h minus 1 minus 2x squared minus x minus -1, which is plus 1. Basically, everything in f of x is going to cancel out. Here's my 2x squared minus 2x squared. Here's my x minus x is 0. -1 plus 1 is 0. So what I'm left with are these 3 terms. All over h. And if you notice that all 3 of these terms have at least one h in them, I can factor out that common h and cancel it with the denominator. But I have to cancel it in its factored form. I can't cancel it until it's factored. Like that. This is my final answer. So this doesn't look like slope, but this is the slope between any 2 points that are h units away from each other on this particular function. In the future, you'll let h shrink to 0, and you'll notice, look, if h became 0, if I replaced h with 0, I would have the slope 4x minus 1. That's basically the slope of any point. If I know what x is, I can tell you the speed of something that's like traveling at this, like following this function. I can tell you the speed just by if you tell me the x, 4x minus 1 is going to be the instantaneous speed. So you don't need to know all of the y. And so you might be thinking, why tell you? But I'd rather know I'd rather know exactly what's up. Like if I were you guys, then I would rather know exactly what's up than just be told, here's some steps, do them. All right. I got a question like, is this homework due tomorrow? Yes, it is. I think you're going to find this homework goes pretty darn quickly. Most of what we did for this homework was learned on Tuesday. All right. Just this like kind of slope stuff is what was added. If you need more time, just use a late pass. And if you need me to add a couple late passes because we've had some funky stuff, just email me. I don't mind adding a couple of them. So that's what I got for you, all right? Are there any questions before I stop recording? Remember, I can't hear you, so you have to use chat. You guys are dismissed. It's the end of our class. 5 minutes early. Makeup, yes, dance. You'll have to, oh, bye. Bye, guys. And so if you do want to stay, I'm here to, I can help you on chat, like I said. Sorry, I can't hear you. You know what I should have done? Here, I'm going to stop recording. I should have just